Hello and welcome to our international free webinar. Once again, I'm Umi Salma, core volunteer and head of campus ambassador in IGP. First, I want to thanks to you all for joining with us in this wonderful evening. Now, before starting our program, let me tell you about IGP. Institute of Global Professionals is an non-profit institution. We organize our webinar training offline, online courses, etc. by best trainer, speaker, coaches from all over the world to create a best learning platform for you all. Our mission is to empower people and enhance skills. So let's start our program with IGP's mantra, feed your skills. Today our 85 webinar organized by on audience most demandable subject mathematics with honorable twin speaker Johnny B. Grape and BENMARC C. Marlano. Topic on trigonometry and algebra. Today our first speaker will give his speech and presentation topic on circle, and he is licensed professional teacher, professional regulation commission and teacher 1. So please give a warm welcome to Sir Johnny Sir. Hello
Hello.
sir.
Yes, hello. Should I introduce myself now?
Yes sir.
Hello, I am Johnny Grafe, and I'm going to be your first speaker for tonight. I'm a graduate of Bachelor of Secondary Education with specialization in mathematics, and I'm currently completing my units for Master of Arts in Education with the same specialization. I'm currently working for the Department of Education, Republic of the Philippines, as a junior high school teacher, and also a dance enthusiast and a choreographer. Now, being a dance enthusiast and a choreographer, I believe that solving math problems is just like dancing. It's a skill that requires confidence, and that confidence can only be achieved or attained through constant practice. Now, I hope that with my talk tonight, I will be able to provide ample practice for you to be able to learn my topic. So again, I'm Johnny Grafe, and I'm going to be your first speaker tonight. So,
So now stage is over to you. You can present your presentation.
okay, I may begin. Okay, so again, good evening to everyone. Good day to the different parts of the world. And for this talk, I'm going to be talking about circles. Okay, um, specifically, I'm going to be talking about the definition, its definition, and different related terms. Of course, we're going to focus also in theorems. I've tried to compress the different theorems into few so that we it would be easier for us to remember all of them. I hope it's going to make sense later. And of course, there will be some practices, some exercises on the applications of these theorems. Okay? Now, if you're ready, let's talk about the definition. What is a circle? Well, it is said that a circle is a set of points in a plane equidistant from a fixed point called the center. So here is a circle, and we're saying it's a set of points on a plane that are equidistant. When we say equidistant, they are of equal distance from this fixed point called the center, and that is point A. Now we name a circle using its center, which is point A. Now we can call this circle circle A. Now, as I said, it's a set of points in a plane that are equidistant from a fixed point called the center. Other definition says it's a closed curve whose all points are equidistant from the fixed point. All right. And this circle now, or every time we have this set of points, this circle will divide the points in the plane into three. Okay. First will be the exterior points. So those points that are left outside the circle. So here we have point B, point C, and point D as exterior points. We also have the so-called interior points, and from the name itself, interior are those points that are inside the circle. So here, point A, which is the center, is also an interior point, and also here we have point E, and there are so many points, infinite number of points inside that circle. And of course, the third one are points on the circle. So here we have point G, a point on the circle, and point F, another point on the circle. Now, it's important to use that word on, especially in dealing with the different definition of terms that are related to circles. Okay, talking about these related terms, let's talk about radius. So radius is, sometimes they say it's a segment or it's a distance from a point on the circle to its center. So here we have point B, a point on the circle, and A as the center. Connecting these 2 points will give us the radius. So we can say AB is a radius of circle A. And in plural, mean two or more radius will be called radii, spelled as radii. Okay. So again, radius is the segment joining a point on the circle to its center, or it could also be said as the distance between the center to any points on the circle. Chord is just the segment joining a point on the circle to another point on the circle. So here in the figure, we have point C, a point on the circle. Another point is point D, another point on the circle. Connecting these two will give us a chord. CD is a chord of circle A. Now we can also have here E, another point on the circle, and we can actually connect it with D, which is also a point on the circle. With that, we can say that ED is a chord. But notice that ED is a chord that passes through the center, which is A. So with that, we can say that ED is a diameter. We can describe a diameter as a chord that passes through the center. Then let's talk about arcs, or arc is actually a part of the circumference of a circle, and it has three kinds. First is a minor arc. A minor arc is an arc that is actually measuring less than half the circumference of a circle. So it will divide the circumference into half, into halves. If the measure of the arc is lesser than that or lower than that, then it's a minor arc. An example here is arc DB. Arc DB is a minor arc. We usually name a minor arc using two letters, its endpoints. So DB or arc DB is a minor arc. Another example is arc DC or arc CD. It's another minor arc. Arc CE as well as arc BE. Okay. Then if we have minor arc, we have the so-called major arc. And if minor arc measures less than half the circumference of the circle, major arc would mean an arc measuring more than or greater than half of the circumference, or half greater than half of the circumference of a circle. Now here we name a major arc using three letters, but make sure we begin and end with its endpoints. For example, we can have here major arc BDC or CDB. That's the same. Again, notice that it measures more than half of the circumference. Another example is arc. We can name this major arc as arc CED or CBD. Again, just make sure you begin and end with its endpoints. All right. And the middle letter should be one of the points where the arc will pass. And of course, the last one is a semicircle. Semicircle, from the name itself, semi, which means half, half of a circle. Okay? This measures exactly half the circumference of a circle. We also name a semicircle using three letters. So here we can say that arc EBD is a semicircle. Another one is arc DCE, also a semicircle. Okay, so we have line segments, radius, chord, diameter, and then we have arcs, minor arc, major arc, semicircle. Now let's talk about angles. We're going to be talking about two kinds of angles here in the circle, or angles that are related to circles. Central angle. We can define a central angle as an angle whose vertex is at the center. So from the name itself, central angle, its center is, or its vertex is at the center of the circle. So here, we can also say that its sides contain radius or radii. Okay, its sides are radii. Here, AB is a radius, AE is also a radius, and they form an angle, a central angle, whose vertex is at the center, of course, which is point A. We have here angle EAB as a central angle. Another central angle is angle BAD. Then, if we have central angle, we also have the so-called inscribed angle. Well, an inscribed angle has its vertex on the circle. Again, we remember these points that are on the circle. So if you have an angle whose vertex is on the circle and whose sides contain chords of the circle, then it is an inscribed angle. So here we have chord CD and chord or diameter ED, and we can have its vertex at D, a point on the circle. Then we can have angle CDE as an inscribed angle. So again, we have segments or line segments, arcs, angles. Then we're going to talk about lines that are related to circle. We have the so-called secant line. A secant is a line that will pass through the circle at exactly 2 points. Okay, exactly 2 points. So here we have the line CD, and notice that it passes through the circle at exactly 2 points, points C and D. Another one is line EB, which is also a secant line that passes through the circle at exactly 2 points, E and B. Of course, if we have the secant line, we also have the tangent line. And a tangent line is being defined as a line that will pass through the circle at exactly 1 point. We call that point a point of tangency. Okay, so here we have a line that passes through circle A at point D. Then we can say point D is a point of tangency. Another example is a line that passes through circle A at point C, exactly 1 point. Now, point C is now called a point of tangency. Okay, I hope everything's clear about the different related terms and its definition about circles. Let's proceed to the theorems. As I said a while ago, I tried to compress the theorems related to circles into, I think, 9. And we're going to try to derive all the rest from those 9 theorems. But before going to each of these theorems, let's always go back to the basics. Okay, these are basics, postulates and theorems that are related to everything that we're going to be talking about tonight or today. First is that angles in a triangle sum to 180 degrees. Okay, we know that the sum of the interior angles of a triangle is always 180 degrees. And also, if we have angles on a line, right? Sometimes we call it a linear pair, or if there will be more than two, as long as it will form a line when you put them together, okay, these angles will also add up to 180 degrees. Then uh, since all the radii of a circle in a circle are equal, then we can say that whenever we have a triangle whose sides are radii, okay, that we can say that these triangles are, or this triangle is an isosceles triangle. Isosceles triangle is a triangle whose two sides are congruent or equal. Now, we have the last one, angles about a point sum to 360 degrees. And that's why we say that the sum of the interior, or the sum of all the interior angles or angles about a point would always add up to 360 degrees. So if we add all the central angles with no common interior points, that would give us 360 degrees. Okay? Now let's take a look at the different theorems and let's try to do it. Let's try to know it one by one. First one, angle at the center of the circle is twice the angle at the circumference subtended by the same arc. So here we can see an angle at the center, the blue one, and an angle at the circumference, because it's the yellow one, and they are being subtended, both of them are being subtended by the same arc, this arc here where they opens. All right. And so we can say that the angle at the center is twice the angle at the circumference. So if the angle at the center is 120 degrees, that is twice the angle at the circumference. That means the angle at the circumference measures just half of that, which is 60 degrees. Now, just to make it easier to understand, we call this blue angle as a central angle based on our definition a while ago. And we call this yellow angle an inscribed angle. So I tried to rewrite this theorem, which says if a central angle and an inscribed angle intercept the same arc, notice that these two angles are intercepting the same arc, then the measure of the central angle is twice the measure of the inscribed angle. Well, we can also derive from here the different theorems related to the central angle and its intercepted arc. Remember that the central angle is always equal to the measure of the intercepted arc. So if this angle here measures 120 degrees, it follows that this arc also measures 120 degrees. Same goes with the inscribed angle and the intercepted arc. The inscribed angle is half the measure of the intercepted arc. So if this arc measures 120 degrees, it follows that your inscribed angle will measure 60 degrees, or just half of that. Okay, I hope everything is clear here. But sometimes it becomes confusing, especially when cases become like this. So it seems like it's not the same as what we had before, but notice that the blue one here is also is also a central angle, and the yellow angle here is also an inscribed angle. It's just that we're gonna look at the reflex angle here, which measures 224, because we're talking about angles intercepting the same arc. So if your inscribed angle is intercepting this major arc here, uh your central angle should also intercept this major arc here. So this central angle measures 224. Then it follows that this inscribed angle here will measure just half of 224, which is 112 degrees. Okay. Same thing goes with here. It seems like it's a different illustration, but notice that we have here a central angle intercepting this arc here, and an inscribed angle measuring 40 degrees intercepting the same arc as what the central angle is intercepting. So with that, we can again use the relationship between the central angle and the inscribed angle as they intercept the same arc. And we said that the central angle is twice the measure of the intercepted arc, or twice the measure of the inscribed angle. I mean, so if the inscribed angle here is 40, we can say that the central angle measures 80. Well, it looks different, but still, it's the same principle. Again, the three illustrations that we had uh, is or are just applications of the first theorem that we talked about, that the measure of the central angle is half or is twice the measure of the inscribed angle as long as they are intercepting the same arc. Now, same principle applies here. It's just that the central angle here becomes a straight angle measuring 180 degrees. So with that, if your central angle here measures 180 degrees, then this inscribed angle here will measure exactly half of this, which is actually 90 degrees. With that, we can say that an angle in a semicircle is a right angle. All right. Or even though the measure is not indicated, as long as you know that your inscribed angle is intercepting a diameter, okay? A diameter. As long as your inscribed angle is intercepting a diameter, then you can conclude that your central or your inscribed angle is a right angle. So it says here in our second theorem that every angle at the circumference, we say angle at the circumference is an inscribed angle. Every angle at the circumference of a semicircle that is subtended by the diameter of the semicircle is a right angle. Then again, the principle was the same as the first principle that we applied. Okay? Moving on, here we can conclude that it measures 90 degrees. Now, on our third theorem, or for our third theorem, we're going to talk about a cyclic quadrilateral. And a cyclic quadrilateral is a quadrilateral inscribed in a circle, mean all its vertices are on the circle. Okay, so we have here a quadrilateral. Two of its angle measures are given. One is 64 and the other one is 87. But based on our third theorem, it is said that in a cyclic quadrilateral, opposite angles are supplementary. When we say supplementary, their measure or their measures has a sum of 180 degrees, or the sum of their measures is 180 degrees. So if we have here an angle measuring 64 degrees, of course, opposite that angle would be an angle that measures 116 degrees. So they would add up to 180 degrees. Okay, for 87 degrees, as stated here, opposite angles are supplementary. So its opposite angle would measure 93 degrees. 87 plus 93 would give us a sum of 180 degrees. So I hope it's clear. For our third theorem, in a cyclic quadrilateral, opposite angles are supplementary. Now, for our fourth theorem, we can say that inscribed angles intercepting the same arc are congruent. So here we have to observe closely, okay, which are the inscribed angles that are intercepting the same arc. So we can take a look at this violet angle and yellow angle. Notice that these two inscribed angles are actually intercepting the same arc, which is arc CD. With that, we can say that the measure of angle A and the measure of angle B are equal, or they are the same or equal in measure. So if we're going to say that the measure of angle A is 40 degrees, we can also say that the measure of angle B is also 40 degrees. Okay? But notice that we can also have here arc A or angle ACB and angle ADB. Both of them are actually intercepting arc AB. So with that, we can also say that angle C is congruent or equal to the measure of angle D. So if we're going to say that the measure of angle C is 25, we can also say that the measure of angle D is also 25. Well, actually, there's one more angle remaining for our triangle here, for our triangles here. And notice that these two angles are actually vertical angles. So we can say that their measures are also equal. So with that, if all the angles or if the corresponding angles of these two triangles inside the circle are actually equal in measure, then we can say that the two triangles here are actually similar triangles. Okay, they have the same angular measures but different in area. We can say that these two triangles are similar triangles, and from similar triangles, of course, we can derive other properties, but we're not going to talk about that today. Okay, so again, inscribed angles intercepting the same arc are congruent. Moving on to our next theorem, it's the fifth one. A tangent is perpendicular to a radius through the point of tangency. So here we have a violet line as a tangent and the blue segment as a radius. Notice that the radius intersect the tangent line at the point of tangency. So with that, we can say that this radius is perpendicular to the tangent line as long as their point of intersection is the point of tangency. Again, a tangent is perpendicular to a radius through the point of tangency. Well, it's an if and only if statement, which means if the the tangent is perpendicular to the radius, then or if a line is perpendicular to the radius, then we can say that the line is a tangent line. Okay, or we can say that if a line is a tangent line, then it is always perpendicular to the radius through the point of tangency. Again, it's an if and only if statement. You can interchange. Now, we have here for our sixth theorem, we have here tangents from an exterior point. But notice that these two tangent lines contain the same exterior point. Uh, Here for our sixth theorem, it says that tangents to a circle from the same point outside are actually equal in length. So here we have these two tangent segments. Okay, from the exterior point, we're referring to the segment from the exterior point all the way to the point of tangency. Okay, these two segments are actually equal in measure. Again, from that exterior point all the way to the point of tangency, these two segments are equal in measure. Now, the line, just to continue, the line joining the external point to the center of the circle actually bisects the angle between the tangents. When we say bisect, it actually means dividing the angle into two equal parts. So if we have here an angle measuring 60 degrees, if we join the exterior or the external point to the center of the circle, then this 60 degrees will be divided into two equal parts, and it's actually 30 degrees each. Okay, so this angle now from the external point was divided into two equal parts by the line joining the external point to the center of the circle. Now, from here, we can also combine it with the previous theorems that we talked about, saying that actually the tangent line is perpendicular to the radius through the point of tangency. So we can say that uh, when we connect the point of tangency to the radius, it will form an angle measuring 90 degrees. So these two triangles now are both right triangles. And actually, by applying the principle of congruence, we know that these two segments here are equal or congruent because of the previous theorem. This yellow line, of course, is congruent to itself because of reflexivity or reflexive property. Then this line here is a radius, and this another line here is also a radius, meaning these two have the same measure also. So with that, we can say actually that these two triangles are actually congruent by side postulate. Okay. Well, that's just an additional. But with that, we can also say that these two angles, if we have said that these two triangles are congruent, then we can say now that these two angles, angle X and angle Y, are also congruent to each other. Okay. Actually, we can know now its measure following the angle sum theorem, or the sum of the measures of the interior angles of a triangle is actually 180 degrees. With that, we can actually conclude that the measure of angle x here is 60 degrees, as well as the measure of angle y here, also 60 degrees. Second to the last, a radius bisects a chord at 90 degrees. Okay. So a while ago, we talked about a secant line that is perpendicular to the radius, but it does not actually bisect the the secant line because it's a line and it goes all the way to infinity. But here we have a chord, and this chord is perpendicular to the radius. Now, if that's the case, automatic that the radius bisects the chord. Again, when we say bisect, it divides the chord into two equal parts. So meaning, if you know that this angle measures 90 degrees here, or they are perpendicular, you can then conclude that these two segments are now congruent because of theorem number 8, a radius bisects a chord at 90 degrees. On the other hand, if you know that the chord was divided into two equal parts, then you can already conclude that they are perpendicular. Again, it's an if and only if statement. Okay? The radius bisects a chord if and only if they are perpendicular. Okay, that's the another way to say it. Again, I'll repeat. A radius bisects a chord if and only if they are perpendicular. Last, alternate angle theorem. Okay. It says here that the angle between a tangent and a chord. Okay. Here is a tangent and here is a chord. The angle between them is equal to the angle in the alternate segment. So where is the alternate segments here? These two are the alternate segments. So the angle that will be formed by these two segments is equal to the angle between the tangent and the chord. So if we have here x as an angle between tangent line and this chord, then this x or this angle measure will be equal to the measure of the angle in the alternate segment or formed by the other two chords, which is here. So these two have equal measures. The same applies with the tangent line and this chord here. Okay. if we have here an angle um, measuring y value or y as the value of this angle, then this angle measure would be equal, or this angle would be equal to the alternate, to the angle in the alternate segment, which is here. So I hope you can clearly see the pattern. I hope you can clearly see the 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 arrangement of the congruence here. Okay. So that's it. Let's try to have some practice on how to apply these theorems. Later on, for the quiz, we're gonna try to see if you have learned how to apply these theorems. So we're gonna try to look at its applications in different situations. For the first one, we are asked here to find the value of x, but notice that this x here is the measure of an angle that actually intercepts a diameter. And based on the theorem that we talked about a while ago, we can say that the value of x here is 90 degrees, because this is an angle or an inscribed angle that actually intercepts a diameter or a semicircle. All right. So I hope it's clear. So there you go. Second one, we have here a central angle measuring x and an inscribed angle measuring 56. So going back to the relationship that we talked about a while ago, we can say that the measure of x here is 112. We just have to multiply 56 by 2. Or we said that the central angle is just twice the measure of the inscribed angle. Now, for this example, or for this situation, we're going to apply the the theorem about the opposite angle of a cyclic quadrilateral, or a quadrilateral whose vertices are points on the circle. If we'll remember the relationship between these two opposite angles, we said a while ago that these two opposite angles are actually supplementary, meaning they add up to 180 degrees. So with that, we can say that x here is actually 100 degrees. Then here, we are asked to find the value of x again, but it's like the first situation that we had a while ago. Um, we have here an inscribed angle intercepting a diameter. Okay, with that, that would mean the measure of that angle is 90 degrees. Then applying the sum of the measures of the interior angles of a triangle, which is actually 180 degrees, we can find the value of x. And that value of x is actually 48. Again, we said that this angle here measures 90 degrees, and adding 42 and 90 degrees would actually give us 132. But the sum of the interior angles of a triangle, or of every triangle, is 180 degrees. So 180 degrees minus 132 is actually 48 degrees. Okay, this seems a little complicated. Um, let's try. What is the value of x here? Mhm. Okay, so from our presentation, we can say that the value of x here is actually 54. But how did that happen? Notice that uh, we have here an isosceles triangle, because this is again a triangle whose sides are actually radii. So if and we have said a while ago that the radii of the same circle are actually equal in measure. So these two segments are equal in measure. That's why we have here an isosceles triangle. And so with that, we can say that the other angle here is also 36 degrees because base angles of an isosceles triangles are actually equal. Then with that, we can say that the measure of this central angle is actually 108 degrees. How did that happen? Of course, the sum of the measures of the interior angles of a triangle is 180 degrees. So adding all these three would give us 180 degrees. And now we can look at the relationship between this central angle and this inscribed angle. Notice that we have here a central angle and an inscribed angle. Both of them are intercepting the same arc. I'll repeat, we have a central angle here intercepting this arc and an inscribed angle here with a value of x intercepting the same arc. With that, we can go back to the relationship that we had a while ago that says the measure of this inscribed angle will simply be half the measure of of the central angle, or the measure of this inscribed angle is half the measure of the central angle. So with that, 108 divided by 2, or half of 108, would actually give us 54. For this one, okay, we're asked to find the value of a. So how are we going to try this one? What is the value of a here? Um, okay, so it says here the value of a here is 29. But how did we come up to that value? Notice that uh, this angle A here is an inscribed angle that intercepts this arc. And this angle here is also an inscribed angle intercepting the same arc. With that, we just have to know the measure of this angle, and that would give us also the measure of angle A. But we can get that by getting the other angle. And here we can clearly see that it's also 89 degrees because of vertical angle relation. So vertical angles are congruent. So we can say that this angle measures 89 degrees. Then since the measures of the interior angles of a triangle has a sum of 180 degrees, we can say now that this angle here measures 29 degrees. So if this is 29 degrees, then this angle A here also measures 29 degrees because they are intercepting the same arc. Okay? Next example, we have here another cyclic quadrilateral. Again, a cyclic quadrilateral is a quadrilateral whose vertices are on the circle. Okay, so again, we go back to its relationship that its opposite angles actually are supplementary. So what is the value of W here? Okay, to find the value of W, but let's reveal first the answer. It's actually 65. How did we come up to that answer, or how did we get that answer? We just form an equation using W and W plus 50, knowing that they are supplementary. Then we can form an equation saying W plus 50 is actually equal to 180 degrees from the theorem that they're actually supplementary. Then we can say that 2W is actually 130 degrees. That's actually applying the additive property of equality, okay, or subtracting 50 to both sides of the equation, and then dividing both sides by 2, or multiplying both sides by 1/2 would actually give us 65. All right. I think we're down to our last example. And our last example here is a tangent uh, to one of the vertices of an inscribed uh, triangle in a circle. Okay, so what is the measure of x here? What we're going to apply is actually the last theorem that we talked about, theorem number 9. So we have to know the value of this angle here so that we will know the value of that angle x there. But notice that in the given, these two sides are marked, which means these two sides are actually congruent. And triangle BCD is an isosceles triangle. With that, again, we can apply that base angles of an isosceles triangle are congruent. So with that, we can say that this angle D also measures 64. And with that, we can say that the value of x here is also 64. So that's it. I hope I was able to provide enough example for you to be able to apply the theorems that we talked about. Sir Ben would actually continue our discussion with his techniques in making trigonometry an easier one. Later on, we're going to have a quiz regarding what we talked about now. Thank you so much.
Thank you, sir, for your entertaining and enlightening presentation on circle. We learned a lot from you, sir, and I think audience will be covered educational sector about this topic. Thank you, sir.
Thank you so much also.
Today, our next speaker will be give his speech and presentation topic on trigonometry made easy, and he is regional trainer, high school math teacher. So please give a warm welcome to Banma G. Malono, sir. Hello, sir.
Hi, good day, good evening, okay, good morning for the others who is watching this webinar in other places. Okay, so magandang buhay. Yan. So that's how we greet in our school, in our division here in Angeles City. Magandang buhay means good life. Okay, so let me repeat that one. Magandang buhay. So when you saw your colleague, you greet him or you greet her with that phrase. Magandang buhay. Okay? So I am Sir Ben. I am a mathematics teacher at Angeles City National High School. So I would like to take this opportunity to thank Sir Nestor Nuesca for giving this opportunity, and also Ma'am Malang, our our supervisor in mathematics, for this rare opportunity to share my knowledge not only in our country but also in other countries as well. Also, I would like to thank Sir Ike Prudente for giving me the go signal to share this topic. I've learned this topic from his webinar last year, and I am so lucky that I attended that webinar and I learned so much, and I'm so much excited to share this one to you. Okay? So let us start this webinar. Okay? So this webinar will focus on the identities. So identities, it focus more on the subject trigonometry. Okay, so to be specific, the topics will be common difference identities, double angle identities, and half angle identities. So for those who already have an idea about this topic, you might think that I'm going to discuss the formulas. So these are the formulas. As you can see, for those who are not yet familiar with these identities, you will see the formulas somehow confusing. Yes, they are easy to memorize for some, but not for all. This is so confusing. Okay. Those are the formulas for the sum and difference identities. Then we also have double angle identities. And then we also have these half angle identities. So counting all of those formulas, we have 16 formulas. If you are a student, if you are not that, if I may say, you are not a math enthusiast, you will really have a hard time memorizing those 16 formulas. Now, in this webinar, the topics that I'm going to share to you right now, guys, is somehow, if I may say, an easier, much easier way in dealing with sum and difference identities, double angle identities, and half angle identities. Okay? So let us start with this example. So sum and difference identities. So suppose that alpha and beta are angles in standard position with sine alpha is equivalent to 4/5 and cosine beta is equivalent to -5/13, where alpha is in the first quadrant and beta is in the second quadrant. Determine the value of sine alpha plus beta and cosine alpha plus beta. So just like what I've said a while ago, we are not going to use a formula here. So the first thing to do here is to somehow illustrate the given example here. So we have here a Cartesian plane. So let's start with the first angle, alpha. So in that case, we're going to draw a triangle. So the angle here would be that one. Okay. So let me use a pointer here. Okay. So this one, this is alpha. And then it says here that sine alpha is equivalent to 4/5 or 4/5. So it means that applying the trigonometric ratio, 4 is actually the opposite side of alpha, while 5 is actually the hypotenuse. Then, for us to identify this side, the measurement of this side, we're just going to use the Pythagorean theorem. Okay? So, applying that theorem, we will get 3 for that side. So, triangle, the first triangle is already complete. For the second triangle, we'll do it this way. So, it says here that beta is in the second quadrant. So, that triangle will be on the second quadrant. So, this is the angle. So cosine beta is equivalent to -5/13. So in that case, cosine, applying the trigonometric ratio, 5 will be the adjacent side, while 13 will be the hypotenuse. Remember this one, in in a Cartesian plane, the hypotenuse is always positive. So in that case, 5 will be the negative number. In that case, this part will be -5, and then the hypotenuse will be 13. For us to identify this part, definitely we're just going to use the Pythagorean theorem. So applying that theorem, we will get 12 for that side. Now, the triangles are now complete. The next thing to do is to create a table. So how are we going to create a table? This one. Okay, so focus on the sequence of the words. The first one, the first one would be angle, and then the adjacent side, and then the opposite side, and then the hypotenuse. And then for the first column, we will write the angles: alpha, beta, and alpha plus beta. For those who are watching right now, I am requesting you to somehow get a paper or a scratch paper and a ball pen so that you can write the table. You can copy the solution here, because later on, we're going to give certificate for those who will get will give certificates for those top 3 scorers. Okay, so the questions for later will be focusing on the discussion right now. Okay, so I'm going to use Kahoot for the online quiz later. So again, get your paper and your writing material so that you can write the solutions for this one. Okay, so again, just like what I've said a while ago, the questions later will be focusing on the examples that I am presenting right now. Okay? Now, for the adjacent side, opposite side, and the hypotenuse of alpha, that is just simply 3, 4, 5 respectively. For beta, same, -5, 12, and 13. Now, if we want to add the angles and we want to identify the adjacent side, the opposite side, and the hypotenuse of alpha plus beta, this is the thing that we're going to do. Follow this one. First, we're going to multiply these two numbers. So 3 times negative 5 is, okay, you are correct. That is negative 15. Next, we're going to multiply these two numbers. 4 times 12, that is, okay, you are correct again. That is 48. And then, for adding angles, what we're going to do with the adjacent side is we're going to add the two products. So we will have now negative 15. We're going to subtract the two products. Okay, so we will now have negative 15 minus 48. And what will be the answer? Okay, you are correct. So that would be negative 63. So for the opposite side of alpha plus beta, this is the process that we're going to do. You multiply these two numbers. Okay, so 4 times negative 5, that is, okay, you nailed it. So that is negative 20. Next, you multiply these two numbers. So what will be the answer? Okay, you got it right. So that is 36. And then we're going to proceed to addition. So negative 20 plus 36. Okay, you are in a row. So that is 16. For the hypotenuse of alpha plus beta, what you're going to do here is just multiply the hypotenuse of alpha and beta. So 5 times 13, and that will be correct, 65. Now, looking at the table right now, we already completed the adjacent side, the opposite side, and the hypotenuse of alpha plus beta. So how are we going to identify sine alpha plus beta and cosine alpha plus beta? So by applying now the trigonometric ratio. Isn't it that sine is equivalent, or sine theta is equivalent to opposite over hypotenuse, while cosine theta is equivalent to adjacent over hypotenuse. So we're just going to apply that concept. So in that case, sine theta now, or sine alpha plus beta now, will be equivalent to its opposite over hypotenuse, and that will be 16 over 65. That's it. And for cosine alpha plus beta, that would be adjacent over hypotenuse. So adjacent will be negative 63, and the hypotenuse is 65. So the answer now will be negative 63 over 65. That's it. So we identify the value of sine alpha plus beta and cosine alpha plus beta without using that formula. So that is the good thing about this process. We do not need to memorize 16 formulas as I've presented a while ago. What we need to remember is only the process. And come to think of it, we are just simply using basic concepts, basic skills. How did we get negative 63? We just simply multiply two numbers and then subtract. How did we get 16? We just simply multiply two numbers and then add. How did we get 65? We just simply multiply numbers. So what are we just simply using here is actually addition, multiplication, and subtraction of integers. As simple as that. And then applying the concept of 6 trigonometric ratios. Okay? So comparing this method in memorizing the formulas, for me, I can see that this is a lot easier. And I think maybe 90% or maybe 80% of those who are watching right now will agree to me that this one is a lot easier compared to the, if I may say, the old method. Okay? So, how come this process is applicable? Let me show you the proof for that one. Okay? So, say for example, we want to add angle alpha and beta. So, for me to add that one, we're going to construct a figure so that they will be combined. So, that figure would be this one. Okay? Now, just going to label the vertices. And then, our goal here is to create a right triangle wherein it consists of the angle alpha plus beta. So in that case, we will have this broken line. Okay? So focus on this triangle. In this triangle, we need to identify the measurement of RS and OS. As you can see here, I marked the right angles here so that later on I will show you the proof, it will be somehow more easier to understand. Okay, so again, our goal here is to identify the measurement of OS and RS. Now, what concept are we going to apply here? We're going to apply the concept of similar triangles. Okay, so let us start with this one. So we know that OS plus SP is equivalent to OP. So that is the segment addition postulate. OS plus SP. OS plus SP is equivalent to OP. Okay? Now, OS, again, just like what I've said a while ago, we need to identify the value of OS. So OS is equal now to OP minus SP. So we apply here the addition property of equality. So we added negative SP on both sides of the equation. Okay. Now, notice this one. PQ is equal to SP. Why? PQ is equal to SP simply because this one is a rectangle and the opposite sides of a rectangle, the opposite sides of a rectangle, they are equal. So in that case, by substitution, we can now say that OS is equivalent to OP minus PQ. Next, OS now is equivalent to 12 minus TQ. So OP, the measurement of OP is 12. Okay, based from this part. Okay, now we can now say that triangle OPQ is similar to RTQ. Why? Definition of similar triangles. Two triangles are similar if their corresponding angles are congruent and their corresponding sides are proportional. Now, look at this triangle. OPQ, where is OPQ? OPQ, the bigger triangle, this one, okay, is similar to RTQ, this triangle. Now, how are they similar? This one is equivalent to 90 minus beta. And applying the vertical angle theorem, this one will be also 90 minus beta. Since this is a right triangle, this part only is equivalent to beta. Again, this is a right angle. So this one, by angle addition postulate, this will be 90 minus beta. And definitely, this will be beta. So in that case, I showed you that triangle OPQ is similar to triangle RTQ. Now, since they are similar, we can say that their corresponding sides are proportional. So in that case, we can now say that PQ over TQ is equal to QO over QR. So PQ, where is PQ? This one, PQ over TQ is equal to QO, the hypotenuse, over QR, the hypotenuse of the smaller triangle. Now, let us substitute the values of each segments. PQ is equivalent to 9. And then we need to identify TQ. So TQ still will remain that one. QO now, the measurement of QO is 15. And the measurement of QR is 8. Now, solving for the value of TQ, it will be like this. So 9 times 8, that would be, correct? That would be 72. So TQ now will be equivalent to 72 over 15. So I won't express that fraction into lowest term. Later, you will see why. Now, substitute PQ by 72 over 15. So OS now will be equal to 12 minus 72 over 15. And solving that one, OS now will be equal to 108 over 15. So remember that one, OS is equivalent to 108 over 15. Let us proceed. So we already have the value of OS. Let us now identify the value of RS. So same process. RS is equivalent to RT plus TS. RS, this whole broken line, is equivalent to RT plus TS, okay, by segment addition postulate. Next, TS is equal to QP. So this is a rectangle, right? So that means that we can substitute TS by QP. QP is 9 based from this illustration. Now, let us identify the value of RT. How? Using the what do you call this? The concept of similar triangles. So RQ over OQ is equal to RT over OP. So RQ, the measurement of RQ is 8. OQ is 15. RT, that's the one that we are identifying. So RT will remain the same. OP now will be equivalent to 9. OP is 12, I mean. So solving for RT now will be equivalent to 8 times 12 over 15. And simplifying that one, that will become 96 over 15. So we already have the value of RT. What are we going to do here? Change the value of RT by 96 over 15. So 96 over 15 plus 9. So that will be 231 over 15. And that is the measurement of side RS. Now, focus now on this triangle. The one that I marked as the red triangle right now. So removing the excess parts. Okay. Now, this is now A plus B. So that's our goal. Now, what's the measurement of RS and OS? Okay. That's great. You still remember the measurement of those two sides. Now, what we do here is we want the sides to be integral, meaning the numbers or the measurement of the sides must be an integer, or if I may say, I mean a whole number. Okay, so it starts from 1 to positive infinity. Okay, so what are we going to do here is to multiply the three sides by 15. The triangle, even though I multiply it by a number, it won't change the triangle itself. It will change, yes, it will become bigger, but still this triangle and the new triangle that will be produced are just simply similar. Okay, so nothing to worry about that one. So let us multiply the three sides by 15. So in that case, ayan. So the measurement of the sides will be 108. To the adjacent side of A plus B or alpha plus beta is 108. The opposite side of alpha plus beta is 231, and the hypotenuse will be 255. Relating it to the table a while ago, we can still achieve this one. How? Let us apply the one that I did a while ago. So first, multiply these two. So 15 times 12, and then multiply these two also. So 15 times 12, that is 180. 8 times 9, that is, okay, you are correct, 72. And then proceed to, okay, that's great. You remember it clearly. We will proceed to subtraction. So 180 minus 72, you are correct again. So that is 108. Okay, next, for us to identify the opposite side, we multiply these two first. So 8 times 12, okay, you are correct, 96. And this one, we multiply these two numbers. Okay, you are again correct. That is 135. And then we proceed to, okay, nice one. That will be positive. So we will proceed to addition. So 96 plus 135, and that will be great. So that is 231. If you will notice, we are arriving at the same answers, comparing the answers from the figure that you are seeing right now. And definitely the hypotenuse, what are the numbers that we are going to multiply to identify the hypotenuse? Okay, correct. We are going to multiply the hypotenuse of alpha and the hypotenuse of beta. So that will be 17 times 15, and that will be 255. So the process itself, it really works, okay, by using the concept of similar triangles. Okay, let us proceed. Now, if we want to deal with the difference of two angles, okay, so the different isn't it that we are dealing here with sum and difference identities. The one that I've explained a while ago is the sum identities. Right now, the difference identities. The process here is just simply the same. The way we prove sum identities is simply the same with the proving of the difference identities. Now, for the process, still the same. The numbers that you will multiply, they are just the same. The only difference will be the signs. Okay? So when we are subtracting the two angles, for the adjacent side, we will add the products. For the opposite side, we will subtract the products. While for the hypotenuse, it will be the same. Okay? So in that case, if we want to identify the adjacent side of alpha minus beta, that would be 180 plus 72. That would be, okay, you are fast. So that would be 252. And for the opposite side, and that will be negative 39. So let us have an example regarding the difference identities. So let us use the same, what do you call this? The same example a while ago so that we can maximize the given example. So let us identify the value of sine alpha minus beta, the value of cosine alpha minus beta, and the value of tangent alpha minus beta. Okay? So in that case, let us apply the concept of the difference identities, I mean. So in that case, so how did we get negative 15 here? We multiply these two. How did we get 48 here? We multiply the two opposite sides and then we proceed to addition. How did we get negative 20 here? We multiply these two numbers. We cannot interchange these two, ha? Okay? So we multiply these two numbers and that would be negative 20. How did we get 36? That is 3 times 12. And then we proceed to subtraction. For the hypotenuse, we achieve 65 by just simply multiplying 5 and 13. So simplifying this one, that would be 33 and negative 20 minus 36. That will be correct. Negative 56. We now have the adjacent side of A minus B. We now have the opposite side of alpha minus beta. We now have the hypotenuse of alpha minus beta. We can now easily identify the value of sine alpha minus beta, cosine alpha minus beta, and tangent alpha minus beta. So applying the trigonometric ratio, sine theta is equivalent to opposite over hypotenuse. So the opposite side is negative 56. The hypotenuse will be 65. For cosine, let us apply that. Again, the trigonometric ratio, cosine theta is equivalent to adjacent over hypotenuse. So in that case, okay, you are correct. That will be 33 over 65. And last, for tangent alpha minus beta. Okay, so I am very much confident that you already know how to do this one. Tangent alpha minus beta will be equivalent to, correct, negative 56 over 33. Okay, so as you can see, it is really easy. Compare it to memorizing 6 formulas. Okay, let us now proceed to another examples. So let us identify the exact value of cosine 15. If you're going to use a calculator, you can already identify the value of cosine 15 degrees. But definitely in a classroom setup, most of the classes are not allowed to use calculator. Okay, so how are we going to identify the value of cosine 15 without using the formula and without using the calculator? So we know that cosine 15 is actually the same with cosine 45 minus 30. So in that case, what we're going to do here is to apply the concept of difference identities. Okay, so let us create a table. So the adjacent side of a 45, the adjacent side, the opposite side, and the hypotenuse of a 45 degree triangle, 45, 45, 90 triangle will be like this. 1, 1, square root of 2. While for a 30, 60, 90 triangle, the adjacent side of a 30 degree angle, the opposite side of a 30 degree angle, and its hypotenuse will be square root of 3, 1, and 2. Now, since we are subtracting two angles, what we're going to do here is to first multiply these two numbers, and that would be, correct, square root of 3. Next, correct, we multiply these two numbers. That will be 1. And then proceed to, okay, correct, you remember it very clearly. So that is, we proceed to addition. Next, for the opposite side of 15 of a 15 degree angle, so what we're going to do here is to multiply these two. I'm sorry for that one. I just carried away. Since we are just simply identifying the value of cosine 15, we don't need to identify the opposite side of a 15-degree angle. Why? Since cosine is equivalent to adjacent over hypotenuse, we don't we don't use the opposite side. So to save time, we will just simply identify the hypotenuse of a 15-degree angle. In that case, multiplying those two, that would be 2 square root of 2. Now, cosine na 15 will be equivalent to adjacent. So that is square root of 3 plus 1 over hypotenuse, which is 2 square root of 2. So what we're going to do here is to simplify this one. So we rationalize that fraction. We multiply the numerator and the denominator by square root of 2 over 2. No worries, we are not changing the value simply because we are just simply multiplying that fraction by 1. Square root of 2 over square root of 2 is equivalent to 1. So we are actually applying the identity property of multiplication. In that case, that will be square root of 6 plus square root of 2 over all over 4. Next example. So what is the exact value of sine 255 degrees? So in that case, sine 255 degrees is actually equivalent to sine 135 plus 120 degrees. So how do we identify the numbers to be added? Think of the special angles. Okay? Think of the special angles. So that's how you identify the two numbers to be added. So let us create a table. So for the adjacent side, the opposite side, and the hypotenuse of a 135-degree angle will be -1, 1, and square root of 2. This is actually the same. Actually, 135 degrees is actually a 45, 90 right triangle in the second quadrant. Same thing with 120. 120 is actually what do you call this? The same with 60 degrees only in the second quadrant. So for 120 degrees, the adjacent side, the opposite side, and the hypotenuse will be this one, -1, square root of 3, and 2. Now, we add the angles. So we multiply these two first, and then these two. So we will now have 1. Sorry. So I'm just simply used to completing the table. So since we are identifying sine 255, we are only after the opposite side and the hypotenuse. So we will not use the adjacent side. So for us to identify the opposite side of 255 degrees, we're just going to multiply those two numbers, 1 times -1, and that would be correct, -1, and then we multiply these two numbers. So -1 times square root of 3, and that would be negative square root of 3, and then proceed to, correct, we are going to proceed to addition. For the hypotenuse, same process, we just simply multiply these two numbers. Square root of 2 times 2, and that would be 2 square root of 2. Now, let us identify the value of sine 255. So sine 255 is equivalent to its opposite over hypotenuse. So in that case, that would be -1 plus negative square root of 3 all over 2 square root of 2. So in our numerator, we can factor out the negative sign. So we can factor out -1. So this one will become -1 plus square root of 3 all over 2 square root of 2. Rationalize that one. So multiply the numerator and the denominator by square root of 2 over square root of 2, and we will get negative square root of 6 plus square root of 2 all over 4. Let us now proceed to the double angle identities. For double angle identities, I'm not going to introduce a new process here. Why? When we, see for example, if we want to double a number, isn't it that we are just simply adding a number to itself? Okay, so in that case, double angle identities is just simply using the sum identities, the first example that I presented a while ago. So let's proceed to the example using the double angle identities. So if tangent x is equal to 2 and cosine x is less than 0, identify the value of sine 2x and tangent 2x. So same process from the sum identities. So let us create a table and let us use this Cartesian plane. Okay. So for the Cartesian plane, it says here that tangent x is 2. So it means that tangent x is positive. Tangent is only positive at the first quadrant and the third quadrant. The other condition is that cosine x is less than 0, meaning cosine is a negative number. Cosine is negative in the second quadrant and the third quadrant. So in that case, these two will meet at the third quadrant. That is why our triangle is drawn like this. Okay? So this will be x. Tangent x is 2 over 1. Tangent x, 2 will be the opposite side, 1 will be the adjacent side. So in that case, since we are on the third quadrant, the adjacent side would be -1. The opposite side will be -2. While the hypotenuse, we're just going to apply the Pythagorean theorem. So in that case, our hypotenuse now will be square root of 5. So in that case, let's just fill this table. Okay, so adjacent is -1, opposite side will be -2, the hypotenuse would be square root of 5. Same thing with this one kasi simply because they're just the same, x and x. So in that case, the adjacent side, opposite side, and hypotenuse are just the same. So let us use the process a while ago. We multiply these two numbers, that would be 1, and then multiply these two numbers, correct? That would be 4, and then proceed to, correct, minus. So 1 minus 4, that will be, you're correct, -3. Next, for the opposite side of 2x, so we multiply these two numbers. So that would be, okay, you are correct, 2. And then multiply these two numbers. Okay, you are also correct. That would be 2. And then proceed to, okay, you nailed it right, addition. So 2 plus 2, and that will be 4. And then for the hypotenuse of 2x, we simply multiply these two numbers, and we will get, correct, 5. So you will notice here that these three numbers are actually Pythagorean triples. Same with the numbers that we attained a while ago. The numbers that we are attaining on the last row are all Pythagorean triples. Okay? Now, let us now identify sine 2x and tangent 2x. Sine 2x is equivalent to opposite over hypotenuse, and that would be 4/5. For tangent to x, that would be opposite over adjacent, and that would be, correct, -4/3. Okay? Next, we are down to our last topic, half-angle identities. For half-angle identities, it is somehow different. Okay? The process here is somehow different from the first three. Okay? Let me show you why is it different. So for half-angle identities, so for the adjacent side, say for example, the adjacent side of a given angle is x, the opposite side of a given angle is y, and the hypotenuse of a given angle is r. The adjacent of half of that angle will be x plus r, the opposite will be just the same, and for the hypotenuse, we will just simply use the Pythagorean theorem. Now, Sir Ben, how come that the adjacent side of a or alpha over 2 is x plus r, and the opposite side of a over 2 is just the same with the opposite side of a or alpha? Let me show you. Let us use the concept. Actually, this was discussed by the first speaker a while ago. So we're going to use the concept of a circle. So let us draw a triangle wherein it has the angle alpha. Okay? So that shaded angle, the measurement of that shaded angle is actually alpha. Next, let us draw this triangle. So we will now have two chords. Okay? So notice that that angle, the one that I shaded right now, is actually an inscribed angle. If you still remember the topic a while ago, the measurement of the inscribed angle is just simply half of its intercepted arc, while the measurement of the intercepted arc is actually equivalent to the measurement of the central angle. So in that case, we can say that the measurement of the inscribed angle is just simply half the measurement of the central angle. So in that case, this will be now equivalent to alpha over 2. Okay? Now, Notice this triangle, that red triangle. That red triangle now, this angle now is actually equivalent to alpha over 2, correct? Now, this part is actually the radius of the given circle. So you will notice now that if this red triangle, the adjacent side is actually equivalent to r plus x or x plus r, while the opposite side is actually equivalent to y. So that is the reason why the adjacent side of alpha over 2 is x plus r, the opposite side of alpha over 2 is y. So for the hypotenuse, just like what I've said a while ago, we will just simply use the Pythagorean theorem. Okay? So let us proceed to the example. So we have here this figure. So based from the given figure, determine the value of cosine beta over 2 and tangent beta over 2. So let us create a table. So for the adjacent side of beta, that would be 3. For the opposite side of beta, that would be 4. And the hypotenuse of beta, that would be 5. Now let us apply the formula that I showed you a while ago on the previous slide. For the adjacent side of beta, that would be x plus r. In that case, that would be 3 plus 5, and that would be 8. For the opposite side of beta over 2, same with the opposite side of beta. That would be 4. And for the hypotenuse, we're just going to apply the Pythagorean theorem here. I'm going to give you 10 seconds to identify the hypotenuse. What do you think would be the hypotenuse of beta over 2? Okay, so you are so fast in determining the measurement of the hypotenuse. So the hypotenuse is, yes, you are correct, 4 square root of 5. So how are we going to identify cosine beta over 2? Just simply apply the trigonometric ratio. Cosine is equivalent to adjacent over hypotenuse. So in that case, that would be 8. Sir Ben, how come it became 2 square root of 5 over 5? Actually, that is 8 over 4 square root of 5. Rationalizing that one and then simplifying it, it would become 2 square root of 5 over 5. Sir Ben, how come there is a symbol here, a positive negative sign? Remember this one, an angle, given angle. Say for example, the given angle is A. A is actually equivalent to 360 plus 8, correct? So if you were going to identify half angle of A, say for example, A is in the first quadrant. Half of A is also in the first quadrant. A plus 360, if you get half of that one, that would be located on the third quadrant. So in that case, we will have two values here. One will be positive and the other one would be negative. The concept that is being applied here is actually getting the square root of a number. Say for example, you want to identify the value of square root of 9. We don't just simply say 9. We don't just simply say 3, but we say positive negative 3, because 3 times 3 is 9 and negative 3 times negative 3 is 9. So that is the concept that is being applied here. Why is that we have positive and negative sign here? For the tangent beta over 2, that would be opposite over adjacent. So that would be 4 over 8 or 1/2. Okay? So that's it. That is the topic about sum and difference identities, double angle identities, and half angle identities without using a formula. I would like to take this opportunity to inform the viewers about the International Vedic Mathematics Olympiad. So as you can see on our screen, the details, you can screenshot here or you can take a picture of this one, or you can visit the page of Math Advocate Ike, or you can check the page here and also this page. So this will, just like what Sir Ike said to me, there are a lot of questions that focuses on the topics that I've discussed in this webinar. So this is a great chance, great opportunity to show your learnings about this webinar. Okay? So I hope that you learned something, and I hope that you will use this topic in the near future, especially for the math enthusiasts that are watching right now. Okay, so with that, I'm going to share the quiz. So 10-item test. Go to kahoot.com, or you just simply search in Google Kahoot. Then I'm going to share the link. Okay? So just going to stop sharing the presentation. This is actually the end of the presentation. So with that, if I may say, maraming salamat. That is thank you in Philippines. In Kapampangan, dakal pong salamat. Keng pamakiramdam. Okay? So what I've said is, I'm very thankful for those who listen in this webinar. Okay? So stop sharing now. So I'm going to share the link for this one. Okay? So wait. Okay. So waiting for players. So the game, excuse me. So the game pin would be 5821529. Again, the game pin is 5821529. So I hope that you copied the presentation a while ago. You used your pen, your writing materials for the discussion a while ago, because the questions that I'm going to present right now are actually based from the discussion a while ago. So I'm just simply waiting for the players.
Yes, sir. We should allow some time for joining. At
Yes.
least five minutes
Maybe I'm going
more.
to give you about, I think, 2 minutes or 3 minutes is enough. I think that is somehow long. Okay, so again,
Okay,
I'm
okay.
encouraging.
We will start at 40, round 40.
Okay, 9:40. So 3 minutes. So I'm waiting for the others to join the quiz.
Yes, sir. After 3 minutes. Dear participants, you have 3 minutes more to join. So join directly, because you guys already remembered that system already. Which how can you join? Those are who are new, who don't know that about Kahoot. So just browse Google Kahoot, and you can just put the pin and join directly. You don't need to install anything. You don't need any link also. Just go to Google and click Kahoot, and write Kahoot, then put the pin, then you will directly join there.
The quiz competition is a multiple choice type of test. So it has 4 choices. So I am hoping that someone from the viewers will join this quiz. So just try to answer the questions that I've prepared a while ago. Come on guys, you can try to join the quiz. This is easy. So there are 101 joined. Okay, so I think we can now start. It's already 9:40 p.m. here in the Philippines. Okay, so let's start. And 5, 4, 3, 2, and 1. Okay, let us start. So what's the value of sine 15? Next one. So Randolph Viray got it, the top scorer right now. Next, what's the value of tangent 255? Okay. So if you copied the presentation a while ago, if you wrote something, you can easily continue the solutions for those. Okay. Next. So refer to the image here. Suppose that alpha and beta are angles in standard position with sine alpha is equivalent to 4 over 5 and cosine beta is equivalent to negative 5 over 13. Determine the value of tangent alpha plus beta. Okay, next one. Again, refer to the image. Go. Next one. Again, refer to the image because the questions are too long.
I think participants that don't read the questions also. They just push the answer.
The answer is 36 over 85. Next one. Okay, so we are on the sixth item. The answer is 77 over 36. Next one, number 7. Jing has the highest answer streak at 4. So Jing is on fire. Next question. The answer is negative 39 over 252. Next one. We are on the third to the last question. So if tangent x is equal to 2 and x is in quadrant 3, what's the value of cosine 2x? The answer is negative 3/5. Next one. Second to the last question. Refer to the image. What's the value of sine beta over 2? The answer is square root of 5 over 5. And we are now on the last question. So refer to the image, please. So actually, we're just simply identifying the formula for the adjacent side of a over 2. How do we identify the formula for that one? The answer is x plus r. So here are the winners. So for number 3, it's m's, and then for second
It's a
place,
short form. It's a short form of the real name. M's
yeah, I
is short.
think, and the top scorer is Leira.
Leida. Yeah.
Okay,
Top score
so
is
I
Leida
can
Zing and
actually screenshot that one so that um we can give proper recognition to them.
yeah, actually, those three participants, congratulations. First of all, congratulations. Those three participants, please contact with our page inbox with your proper name and gender, with your full name and gender, to directly contact with our page inbox that we can issue the certificate within short time. So it's a request, dear participants, to those first, second, and third. Please directly contact with our page inbox directly to issue your certificate with your full name, with a screenshot of this, and with your gender, so you can issue the certificate within short time. Thank you, Sir Ben. Sir Ben, you can, yeah. And thank you,
Welcome.
Sir Johnny.
Yes, yes.
Actually, sir, at the last time, I think some internet connection issues. So no problem. If we have already time, so we move to the Q&A. Okay, sir. Still no question. That means you discuss the topic clearly. There's the point. So still no question available. Oh yeah, already someone wrote that the speakers are very good.
Thank you.
Dear participants, do you have any question regarding these topics? If you have any question, then directly write in the comment section. We'll put the comment question to our speakers. The discussion is very clear. The topic were present clearly. Uh, Someone asked one thing, is it maybe just to improve the Kahoot part? Actually, it's not our plan. It's not our fault. It's problem from Kahoot. It's internet connection issue. It's not in our side. Yes, one question. You can see the dear speakers. You can see the question on your screen.
So trigonometry can be connected to the real world if you are planning to be an engineer, or if you are planning to have a job that uses trigonometry. But if in case that you are not planning to do that one, how are we going to use trigonometry in real life? We're going to use trigonometry, the skills that we can learn from trigonometry, not the tangent, not the sine, not the cosines, not the triangle, but the what do you call this? The your way of thinking in dealing with those problems. Those things are the things that can be applied in real life situations. Actually, that is the one that I always say to my students. We are not going to use mathematics, not all of them. We're not going to use them in real life, but what we're going to use will be the what do you call this? We're going to use the skills that we learn, patience, patience in doing a certain problem, solving a certain problem. Those are the things that we can really apply in real life situation. For the identities application, just like what I've said a while ago, um, in if I may relate this in our department, the Department of Education, the mathematics is actually what do this the goal of mathematics is to promote critical thinking and problem solving skills. Now, in that way, solving trigonometric identities will improve or will help the students to become a problem solver and to become a critical thinker. How to solve trigonometry word problems, though that question is somehow not that related to the topic that I've discussed, but you can solve trigonometric word problems by actually you can really solve trigonometric problems, but siguro if I may say, how can you solve it in a way, in an easier manner? First, expose yourself to different types of problems that involves trigonometry. Second, practice, practice, practice. So that is the thing that I can share or I can say if you want to be a good solver in trigonometry.
Projecting figures like circles, there are, you mean in teaching, ma'am, we can actually use certain applications, but what I usually use is GeoGebra. Actually, GeoGebra is an application that you can use to graph functions, but you can also use this application to, project circles, to draw circles, and actually even its parts with accurate measurements.
How can trigonometry concepts be applied in this pandemic time? Mm, that's a really hard question, but maybe we can use this trigonometric concepts to, if I may say, killing time. So we can use the things that I've shared to you a while ago to learn something, especially this time that we are not, some of us, or if I may say, most of us are not allowed to go outside, to stay at home. So instead of just simply looking at your gadgets, instead of just simply watching cartoons or watching movies, you may do this one to somehow unlock something new skill, so that in the near future you may use it. Siguro you may use it in a way that you may teach your future children, or you may use this to teach other students who are having a hard time in trigonometry. So we may use this skill during this pandemic.
Thanks, sir, for giving you valuable insight on trigonometry and circle. I think those topics are so important because those topics are used, we find in physics, chemistry, or also in biology. So trigonometry and circles are so important for us, and I expect that audience like it. Thanks, sir, for giving your valuable time and share your knowledge with us. Dear audience, today's webinar is so important and informative for our teacher and students because it is directly and indirectly relatable in education, also in professional life. I hope this webinar will be helpful, and I would love to, congratulations to the winner also, and I would love to thank you all for attending today's sessions. Please give a review in our page, and if we help you or you find any helpful things from our webinar, please spread the information with your friends. If we hope to see you all again in next webinar. Thank you so much. Stay happy, stay safe.